Hi everyone, welcome to another video for Research Design and Analysis. This is our first video in a series when we're talking about models with multiple categorical predictors and talking about one-way analysis of variance, where we have a single categorical factor that has multiple levels. So we have to be able to make a distinction between more than two groups in our statistical analysis. So although we're going to focus on categorical variables later on, it's going to be really useful to start with some continuous variables and think about some of the problems that arise when we have multiple continuous variables in the same regression model. And we're usually going to have multiple variables in our regression model because often conditioning our predictions on a single variable is not going to be enough. And the reason for this, right, is that most variables that we measure, our y outcomes, are going to be, caused by or at least associated with multiple factors. So we couldn't just run, simple regressions all the time and hope to get great explanations of y. More often than not, we're going to have to account for multiple x variables in order to get reasonably good predictions of what's going on in y. The problem with this, however, or at least one of the problems with this, right, that makes this more complicated when we start adding in multiple variables, is that the x's don't only relate to y, but the x's also relate to each other. So for instance, if we think about, the relationship between age and height, and how they relate to weight, we know that both age and height are positively related to weight, right? As you get older, you get heavier. As you get taller, you get heavier. But height is also related to age, because as you get older, you get taller. So then how much of the relationship between weight and height is actually due to age, right? These relationships between the x's and the y also have to take into account that these x's might be related to each other. And then how do we determine, is the part of height and age that's shared, does that count for height? Does it count for age? Does it count for neither of them? Right? We have to take some special considerations into account when we're building these multivariable regression models. So again, let's focus on this continuous relationship for now, although ultimately we want to talk about some categorical variables. But in this example, we're going to look at the relationships between students' heights, weights, and ages for this hypothetical data set of students. And you can see this presented in a three-dimensional scatter plot over here where we have weight on the y-axis, height on the x-axis, and age on the z-axis. And you can see that as students get taller, their weight goes up. Also, as students get older, right, their weight goes up. But importantly, there's also a relationship between our two x variables where as students get as students get older, I should say, they also get taller. So there's positive relationships among all three of these variables that we have to take into account. So when we're going from a univariable model to a multivariable model, right, as you might have guessed, we're going to add an additional predictor into our regression equation, right? So we still are making some prediction about y, represented by y hat. We're going to make some estimate of the intercept. Then we're going to have some estimate of the effect of our first x variable, right? And then we're going to have some estimate of the effect of our second x variable. So this will be the effect of x1 on our y prediction. And this will be the effect of x2 on the predicted y value. Now, if you do this for the data that I actually showed, you run this through, Jamovi or R, your regression program, you're going to get a predicted weight, which gives you then a negative intercept, plus, the slope for the effect of height, plus the slope for the effect of age. So this is telling us then the predicted weight, right, for somebody with a height of 0 and an age of 0, some hypothetical non-existent person, right, the predicted weight is negative 141.22 pounds. However, that's just a starting point. That's an anchor for our regression line. That intercept isn't really meaningful because we don't have anybody who's 0 inches tall and 0 years old. So we can kind of ignore that intercept. We'll just think about it as an anchor point. But these slopes really are meaningful. So we have this height of 3.6 times height. So for every 1 inch taller you get, we're going to estimate that you are 3.60 pounds heavier. And then for every for every year older you are, we're also going to estimate that you're 1.28 pounds heavier. So for every inch taller, you get 3.6 pounds heavier. For every year older, you get 1.28 pounds heavier. And this is what we would get if we ran these data through the regression program. But the question is, how do we arrive at these estimates? How do we actually get the numbers for these slopes? Well, the important thing to consider is that this is the effect of height when we're controlling for age. So if we get this 3.6 value, this is the unique effect of height. So above and beyond age, we think that for every inch taller you are, you're going to gain 3.6 pounds. The other way to think about this is holding age constant, right? Because if I had an 11-year-old versus a 12-year-old, their prediction is going to change based on this slope here. But if I have two 11-year-olds, right, then they're going to get exactly the same product over here. So then what's going to be different is the changes in weight due to their height. So you can think about controlling for the other variable then as it gives you the unique effect of one variable, or it's the effect of that variable holding the other variable constant. And we're going to talk a little bit more about what that means. But also just to point out that similarly then, this is true for the effect of age. This is age controlling for height, right? So this is the effect of age if we held height constant. But how do we arrive at these numbers? Well, one of the issues that we have in this kind of regression model is that we have to control for the shared variance between our predictors. So again, weight is our outcome. So you remember that we always do a sum of squares error total calculation to get the total sum of squared errors in weight. So that represents, this circle conceptually represents that sum of squared errors as an area kind of 1. It's the total variability in the weight variable. Now, there's also going to be some total amount of error or variability, right, in our x variable of height, and there's going to be some total amount of error or variability in our x variable of age. And these things will overlap because, as we said, as you get older, right, you also get heavier. So that's represented by the shared variance between weight and age. As you get taller, you also get heavier. That's represented by the shared variance between height and age. But as you get older, you also get taller. So there's some component of this that's explained by both. And how we handle this shared variance is going to determine the numbers that we get out of our regression model. So you can think about this then if we're controlling for age, right, to look at the effect of height. What we're going to do is mathematically remove the variance that's due to age, and we're going to remove that variance from weight, and we're going to remove that variance from height. And now we're just going to say, okay, the part of weight that is independent of age, how much of that is explained by your height? So now we're looking at this proportion, right, the shared variance out of this total variance. Similarly, if we want to look at the effect of age controlling for height, right, we would remove the variance due to height from both weight and from age. And now that shared variance is again getting excluded. And if we want to say, well, what part of age is independently related to weight, then now it's this area of overlap, right? It's this shared variance is explaining, this part of the total variability due to weight. So after the variability due to height is removed, we can now assess the age-weight relationship more accurately. And this overlapping area then would be the relationship between age and weight when we're controlling for height. So now note that the shared variance gets completely excluded in both cases, and this can be a problem if our two variables are highly related, right? So in this case, it's not too big a deal if we exclude this from height because there's still a lot of height that's independent of age. And it's not too big a deal if we exclude this shared variance from age because there's still a lot of variability in age that is independent of height. But you can imagine if we move these kind of yellow and red circles closer together, that area of overlap is going to get bigger and bigger. And if we're excluding a large area of shared variance, that can actually create some problems for our statistical models. So this introduces the notion of what we call collinearity, or a strong correlation between our x coefficients, right? So one way we can think about this is that I can predict your total height as a function of the length of your left leg. And there's a lot of overlap between these two because taller people very strongly tend to have longer legs, right? So there's going to be a tremendous amount of overlap here. Now, it's not a perfect relationship because there's variability in where people's height comes from. Some people are longer in the trunk, some people are shorter in the legs, right? So there's going to be some variability here, but in general, there's going to be a really strong positive relationship, and the length of a person's left leg is going to be a really good predictor of their total body height. So now you're thinking, can I improve my prediction of total body height what if I also threw in right leg length as a predictor? Well, again, right leg length on its own is probably a good predictor of height and is probably a good predictor of left leg length. But the problem is the correlations between these three variables are so strong that the area of overlap is going to be huge. And that means then that when you actually look at the effect of left leg length controlling for right leg length, it's going to have a tiny, tiny effect, right? It's going to be actually a worse predictor of height now because you're asking about the part of left leg length that is unrelated to right leg length. And that's probably not what we want because that shared variance is actually interesting. It's kind of the key part that's shared between all three of them. So if we are putting in variables that are highly collinear, that can really distort the relationships that we're looking at, because although both of these predictors are good predictors on their own, they become terrible predictors now if we include them in the same model and they have this high correlation between each other. So moving forward, right, we're going to actually focus on situations where the correlation between the x variables is 0 or it's at least trivial, right? So for instance, we're going to focus on experimental designs where participants have been randomly assigned to conditions. So that's going to make the correlation then 0 because we should have equal numbers of people who have been randomly assigned to different conditions. However, if you work with observational data or you start including other covariates in your model, we're going to have to worry about this collinearity. So it's important to bring up this concept now, right? And for the immediate future, we're not going to really worry about it because we're going to focus on designs where there's not a correlation between our x variables. But it is going to be a topic of future courses that you might take and future videos that we're going to cover here, because we are going to have to worry about these correlations between x variables moving forward. Finally, the other thing that we want to note is that this approach to excluding the shared variance is known as the type 3 formulation for the sum of squared errors. There are different types of calculations for the sum of squared errors, and they all vary in how they handle shared variance. The type 3, as we talked about, excludes the shared variance from all variables, right? So it takes the part of age and height that's related to each other, and it removes it from height, it removes it from age, so that you look at the part of height that is independent of age and the part of age that is independent of height. And we like this one because it really allows us to interpret one variable as controlling for all other variables in the model. And it's also very common in a lot of statistical analysis programs. I think most of them will give you the type 3 sum of squared errors by default, but you'll often see this listed in your regression output. It might say, note sum of squared errors equals type 3, or note that sum of squared errors equals type 1, right? Type 1 and type 2 are a little bit less common, but that's not to say they're not important because they are still useful in different contexts. In type 1, the primary difference is that you're actually removing that shared variance based on the order in which the variables are entered into your model. So for instance, if you have height and age in your model, rather than excluding the shared variance from both, the type 1 sum of squared errors will give that shared variance to whichever variable got entered first. So if you say, well, I want to attribute that variance to age, because I think that age is, the natural process that's driving both height and weight, right? Then you might use type 1 sums of squared errors and put age in your model first, then the shared variance goes to age, and then you could add height as a second variable later, right? And now that shared variance belongs to age, not to height. Type 2 sums of squared errors are less common, and they are a little more complicated. They will make more sense once we're talking about interactions between factors and some more advanced models we'll get to later. But I do just want to point out that they do exist. So we'll probably revisit this when we're talking about interactions and the utility of calculating type 2 errors. But the main thing is just to make you aware there are 3 different formulations of the sum of squared errors. Most programs will use type 3 by default, and we will be focusing on using the type 3 sums of squared errors moving forward.